The island of fire and sulfur. In the vast archipelago of Indonesia where the Pacific Ring of Fire burns brightest, there exists a place where Earth's ancient forces paint the night with colors that defy human imagination. This is not a tale of distant planets or science fiction fantasies. This is the story of Kawah Ijen, a volcano that breathes blue fire into the darkness. Java, the heart of Indonesia, stretches like an emerald spine across the equator. At its eastern edge, where the island narrows before surrendering to the Bali Strait, rises the Ijen volcanic complex. Here, a cluster of stratovolcanoes stands sentinel over landscapes sculpted by millions of years of geological violence. Among them, Kawah Ijen distinguishes itself not through height or destructive history, but through a phenomenon so rare that only a handful of places on Earth can claim it. The mountain reaches 2,799 meters into the tropical sky, its slopes draped in dense jungle that conceals the tortured rock beneath. But it is not the summit that draws the eye. It is what lies within. Nested in the volcano's crater, nearly a kilometer wide, sits a lake of such peculiar chemistry that its waters glow an otherworldly turquoise under the sun. This is the largest highly acidic crater lake on Earth, a cauldron of sulfuric acid with a pH approaching 0, where nothing lives and nothing can survive. For centuries, the Javanese people regarded Ijen with a mixture of reverence and fear. They understood, as all who live beside sleeping giants must, that the mountain's tranquility was temporary, negotiable, subject to forces beyond human control or comprehension. Villages dotted the fertile volcanic soils at safe distances, their inhabitants farming the rich earth that catastrophe had blessed with mineral wealth. But Ijen harbored secrets deeper than its acidic lake. Beneath the crater floor, in fissures and vents where superheated gases escape from the magma chamber below, something extraordinary occurs. When sulfuric gases emerge from the earth at temperatures exceeding 600 degrees Celsius, they ignite upon contact with oxygen. The flames that result burn an electric blue, a color so intense and unnatural that early witnesses questioned their own sanity. This blue fire appears only at night, invisible to daylight's glare. It flows like liquid lightning down the crater walls, rivers of cerulean flame that illuminate the darkness with spectral beauty. The phenomenon exists in only 2 other confirmed locations worldwide, making Kawah Ijen a geological marvel of extraordinary rarity. Yet the blue flames represent merely the visible manifestation of deeper processes. The same volcanic vents that produce this ethereal light also deposit pure sulfur, element number 16, in crystalline yellow formations that accumulate in massive quantities. For over a century, men have descended into this toxic crater to mine these sulfur deposits, carrying loads that would break lesser backs up treacherous paths in conditions that mock every principle of occupational safety. The Ijen complex itself sits within a larger caldera, the remnant of a catastrophic eruption that occurred approximately 50,000 years ago. That ancient explosion created a depression 20 kilometers wide, within which newer volcanic cones subsequently grew. Kawah Ijen is one of these younger formations, its current crater a mere infant in geological terms, perhaps only a few thousand years old. The tectonic forces responsible for Ijen's existence operate on scales both vast and intimate. Here, the Australian plate subducts beneath the Sunda plate at a rate of approximately 7 centimeters per year. This collision zone, stretching along Indonesia's southern coast, generates the magma that feeds Ijen and its volcanic siblings. The process is elegant in its brutality. Oceanic crust descends into the mantle, melts under tremendous pressure and heat, then rises again, seeking release through volcanic vents. What makes Kawah Ijen's chemistry so extreme? The answer lies in the unusual composition of its magma and the shallow hydrothermal system that concentrates sulfur compounds. Rainwater percolates through fractured rock, encountering rising volcanic gases rich in sulfur dioxide and hydrogen sulfide. Chemical reactions transform these gases into sulfuric acid, which accumulates in the crater lake, creating a reservoir of corrosive liquid more acidic than battery acid, hot enough to boil at its depths and capable of dissolving flesh in minutes. This is the stage upon which our story unfolds. A place where beauty and danger share the same breath, where economic necessity drives men into conditions that resemble descriptions of hell, and where Earth's elemental forces remain as raw and uncompromising as they were at the planet's birth. Kawah Ijen is not merely a volcano. It is a window into processes that built continents and shaped the very atmosphere we breathe. It is a reminder that beneath the thin skin of soil and civilization, our world remains fundamentally wild, powerful, and indifferent to human presence. Before we continue this story, subscribe to the channel. Your support helps us tell the true stories of Earth's most powerful volcanoes. The architecture of a volcano reveals its character as surely as the rings of a tree reveal its age. Kawah Ijen is a stratovolcano, a term that describes not merely its shape but its biography, its method of construction, its potential for violence. Layer upon layer of hardened lava, ash, and pyroclastic debris have accumulated over millennia, building the classic conical profile that dominates the landscape. This is not the gentle dome of a shield volcano, spreading its lava in patient flows across vast distances. This is a structure born from explosive temperament, from magma that traps gases until pressure demands release. The crater itself measures approximately 1 kilometer in diameter, a vast amphitheater carved by explosions and subsequently filled with water from rainfall and volcanic springs. The lake that occupies this depression contains roughly 36 million cubic meters of acidic water, its volume fluctuating with seasonal rains and evaporation rates. The surface temperature averages around 40 degrees Celsius, but at depth, near the active fumaroles, the water approaches boiling point. Steam rises from these hot spots, creating patches of turbulence on the otherwise still surface, visible markers of the heat engine operating below. The southern crater wall rises steeply, its inner face a mosaic of yellow sulfur deposits, gray volcanic rock, and patches of white sublimate where sulfurous gases have crystallized upon cooling. This wall serves as the primary mining route, a treacherous path worn smooth by decades of foot traffic, often obscured by the very gases that make the journey profitable. The gradient approaches 45 degrees in sections, requiring miners to use their hands as much as their feet, all while carrying loads that would challenge pack animals. Beneath the visible crater lies a complex plumbing system of fractures, conduits, and magma chambers. The primary magma reservoir sits approximately 5 kilometers below the surface, a body of molten rock perhaps 2 kilometers in diameter, fed continuously by the subduction process occurring far below. From this reservoir, smaller dikes and sills branch upward, seeking paths of least resistance through the fractured volcanic edifice. Where these magma bodies approach groundwater, they create hydrothermal systems, superheating the water and loading it with dissolved minerals and gases. The fumaroles that vent at the crater floor represent the terminal points of this system, places where the pressure gradient finally equalizes, where Earth's interior atmosphere meets the exterior. The gases emerging from these vents contain sulfur dioxide, hydrogen sulfide, carbon dioxide, and trace amounts of hydrochloric acid along with water vapor. The sulfur dioxide concentration can reach lethal levels during periods of increased volcanic activity, displacing oxygen and creating invisible pockets of unbreathable air. What makes Kawah Ijen's fumaroles unique is their temperature and consistency. The vents maintain temperatures between 200 and 600 degrees Celsius year-round, hot enough to ignite sulfur gases but not so hot as to prevent sulfur deposition. This narrow thermal window creates ideal conditions for the blue fire phenomenon. When sulfur vapor condenses and ignites, the flames burn with characteristic blue luminescence, a result of sulfur's spectral emission pattern. The fires flow downslope because burning sulfur vapor is denser than air, creating rivers of flame that pool in depressions and illuminate the crater with ghostly light. The chemical processes occurring within the crater lake deserve particular attention. With a pH between 0.3 and 0.5, the lake ranks among the most acidic natural bodies of water on the planet. This extreme acidity results from the continuous influx of sulfuric acid formed when sulfur dioxide dissolves in water. The lake acts as a giant chemical reactor, concentrating dissolved metals including aluminum, iron, and manganese leached from surrounding rocks. The distinctive turquoise color results from suspended particles of native sulfur and dissolved metal sulfates that selectively absorb and scatter light. The lake's volume and chemistry fluctuate with volcanic activity. During periods of increased heat flow from below, evaporation accelerates, concentrating the acids further. The water level can drop by several meters during dry seasons, exposing sulfur-encrusted rocks along the shoreline. Conversely, monsoon rains dilute the lake slightly, though not enough to render it any less hostile to life. Nothing swims in these waters. No bacteria colonize the shores. The lake exists in a state of chemical sterility, maintained by conditions incompatible with even the most extremophile organisms. The monitoring of Kawah Ijen presents unique challenges. Traditional seismometers track earthquakes beneath the volcano, detecting the micro-tremors that indicate magma movement. Gas sensors sample fumarole emissions, looking for changes in composition that might signal rising magma. Thermal cameras track heat signatures across the crater walls. GPS stations measure ground deformation with millimeter precision, detecting the subtle swelling that precedes eruptions. Yet the acidic environment corrodes instruments with ruthless efficiency. Equipment that might last years elsewhere fails within months at Ijen, requiring constant replacement and calibration. The last confirmed magmatic eruption of Kawah Ijen occurred in 1817, though phreatic eruptions, driven by steam rather than magma, have occurred more recently. The 1817 event produced a modest lava flow and ash column, nothing compared to the catastrophic eruptions of neighboring volcanoes. Yet this relative quiescence should not inspire complacency. The magma chamber remains active, the hydrothermal system continues functioning, and the tectonic forces that built Ijen continue their patient work. The mountain sleeps, but it does not rest. Beneath the blue fire and the acidic lake, the machinery of planetary violence remains operational, awaiting only the proper conditions to demonstrate its full capacity. In the dead of night, on the Indonesian island of Java, a spectacle unfolds that seems torn from another world. This is Kawah Ijen, an active volcano, home to a mesmerizing yet deadly phenomenon. Before the sun even hints at its arrival, electric blue flames dance across the landscape, a ghostly fire fed by burning sulfuric gases. But as dawn breaks, the ethereal beauty gives way to a brutal reality, for this otherworldly place is a workplace. It's a mine, and the men who toil here are often called the miners of hell. Our journey begins with a descent into the crater, a path that feels like a gateway to the underworld. The air grows thick, heavy with the sharp, choking smell of sulfur. We follow the silhouettes of men, their worn boots finding purchase on loose volcanic scree. They move with a practiced familiarity, navigating the treacherous terrain in near darkness, guided only by the faint glow of headlamps and the distant flickering blue fire. Each step takes them deeper into a toxic cauldron, where the very air they breathe is a corrosive poison. They carry no modern safety equipment, just a wet cloth held between their teeth to filter the worst of the fumes. This is their daily commute. Reaching the crater floor is like landing on an alien planet. Here, the heart of the volcano reveals its true nature. Ceramic pipes, laid down by the miners themselves, channel molten sulfur from deep within the earth. It pours out as a viscous, blood-red liquid glowing with intense heat before it cools and solidifies into vast fields of brilliant canary-yellow rock. The ground hisses and steams, vents releasing plumes of suffocating gas. All around us is the world's largest acidic crater lake, a stunning yet lethally caustic turquoise pool. The vibrant colors paint a scene of surreal beauty, a stark and terrible contrast to the labor that is about to begin. The work is primitive and punishing. Armed with nothing more than heavy steel bars, the miners attack the freshly hardened sulfur. The air rings with the rhythmic clang of metal against rock. They pry and hammer, breaking the brittle mineral into manageable chunks. The effort is immense. Every swing of the bar sends shockwaves through their bodies. They work quickly, surrounded by a constant fog of toxic gas that stings the eyes and burns the lungs. Once a pile of sulfur is gathered, the loading process begins. The men hoist the jagged, heavy rocks into two baskets linked by a bamboo pole. They carefully balance the load, a skill honed over years of backbreaking repetition. The true test of their endurance is the ascent. With loads weighing between 70 and 90 kilograms, often more than their own body weight, they begin the grueling climb out of the crater. The path is a steep, narrow, and unforgiving track carved into the volcanic rock. Their bodies are bent almost double under the immense weight, their faces etched with a profound strain that speaks of years of this relentless toil. They pause often, not for rest, but to catch a breath of less toxic air, their chests heaving, their muscles screaming in protest. This is a journey they make once, sometimes twice a day. The physical toll of this work is etched onto the miner's very being. We see faces that look decades older than their years, skin weathered by sun and sulfur. Their teeth are often eroded and blackened by the constant exposure to acidic gases. Their shoulders are permanently deformed by the weight of the bamboo poles. At the weighing station, high on the crater rim, the reality of their reward becomes clear. The baskets are weighed, and the miners are paid by the kilogram. The sum is shockingly small, a meager wage for risking their lives in one of the most hazardous workplaces on Earth. This yellow rock, which will end up in cosmetics, fertilizers, and countless industrial products around the globe, is purchased from these men for just a few cents per kilo. As we stand here, surrounded by tourists who have come to witness the blue fire and the spectacular sunrise, the contrast is jarring. For us, Kawah Ijen is an adventure, a photo opportunity, a story to tell. For the miners, it is a daily struggle for survival. It's a choice made out of a lack of other options, a way to provide for their families in a region with few economic opportunities. They are strong, resilient, and surprisingly warm, often offering a smile or a nod to the visitors who walk the same path unburdened. They are fathers, sons, and husbands, trapped in a cycle of dangerous labor for a world that consumes the fruits of their hardship without a second thought. The story of the Kawah Ijen miners is not just one of incredible human endurance. It's a profound reminder of the hidden costs buried deep within our global supply chains. It challenges us to think about the people behind the products we use every day. As the sun climbs higher, casting its golden light over the stunning volcanic landscape, we leave you with one final image: a miner, having delivered his load, standing at the edge of the crater. He looks back down into the smoky abyss from which he just emerged and then out towards the distant horizon. In his gaze, there is exhaustion, there is resilience, and there is a quiet dignity that transcends the hellish conditions of his work. Thank you for joining us on this journey. If this story moved you, please consider liking and subscribing for more documentaries that explore the unseen corners of our world. The phenomenon that draws thousands of visitors annually to Kawah Ijen's rim defies intuition. Fire, in common experience, burns orange, red, or yellow. These colors represent the thermal radiation of carbon-based combustion, the wavelengths emitted when organic materials oxidize at temperatures between 800 and 1200 degrees Celsius. But the flames that dance across Ijen's crater floor burn electric blue, a color so vivid and unexpected that early observers questioned whether they witnessed fire at all or some form of bioluminescence, perhaps a chemical reaction unrelated to combustion. The truth involves sulfur's unique chemical properties and the specific conditions within Ijen's fumarole system. Sulfur exists in multiple molecular configurations depending on temperature and pressure. At temperatures above 250 degrees Celsius, sulfur vapor becomes the dominant form, individual molecules and small polymeric chains floating freely in gaseous phase. When this vapor emerges from volcanic vents into oxygen-rich air, ignition occurs spontaneously. The combustion reaction oxidizes sulfur to sulfur dioxide, releasing energy in the form of heat and light. What makes the flames blue is sulfur's atomic emission spectrum. When sulfur atoms achieve excited electronic states during combustion, they emit photons at wavelengths between 394 and 469 nanometers, concentrated in the blue portion of the visible spectrum. This emission pattern differs fundamentally from the blackbody radiation that produces yellow flames in wood fires or candles. The blue color represents discrete quantum transitions within sulfur's electron shells, a phenomenon observable only when sulfur burns in relatively pure form without contamination from carbon or other elements that would shift the spectral output. The temperature requirements for this phenomenon fall within a narrow range. Too cool, and sulfur vapor condenses to liquid before igniting. Too hot, and the flames burn so completely that minimal sulfur vapor remains to produce visible luminescence. Kawah Ijen's fumaroles maintain this precise thermal window through a balance of heat flow from the magma chamber below and cooling from contact with atmospheric air. The vents emit gases at temperatures between 200 and 600 degrees Celsius, with the highest concentrations of combustible sulfur vapor occurring in the 360 to 480 degree range. The flames themselves flow downhill because burning sulfur dioxide is denser than air. This creates the surreal spectacle of liquid-appearing fire, streams of blue flame that pour across the crater floor, pool in depressions and illuminate the landscape with ethereal light. The flows can extend several meters from their source vents, cooling gradually as they mix with ambient air until combustion ceases and the gases dissipate. During periods of increased volcanic activity, when gas emissions intensify, the blue fire rivers expand, creating larger displays that can be visible from the crater rim even without descending. Only 2 other locations on Earth produce confirmed blue fire phenomena of comparable intensity. Dawa volcano in Ethiopia exhibits similar sulfur combustion, though its accessibility and political instability limit observation. A volcanic area in Iceland shows occasional blue flames during certain eruptive phases, though not with Ijen's consistency. This rarity stems from the specific combination of factors required: high-temperature, sulfur-rich volcanic gases, adequate oxygen supply, minimal atmospheric moisture, and vent configurations that allow sustained combustion rather than explosive release. The chemistry of Ijen's fumarole emissions reveals complexity beyond simple sulfur dioxide production. Gas samples collected at various vents show significant concentrations of hydrogen sulfide, a compound that contributes its own toxicity to the crater environment. At high temperatures, hydrogen sulfide can also combust, producing sulfur dioxide and water, while releasing additional heat that sustains the blue flames. Carbon dioxide appears in moderate concentrations, evidence of magmatic degassing. Trace amounts of hydrochloric acid, hydrogen fluoride, and various metal chlorides indicate interaction between volcanic gases and the hydrothermal system. The blue flames are most visible at night because their luminosity, while intense, cannot compete with sunlight. During daytime, the combustion continues, but the flames become nearly invisible, detectable primarily through heat shimmer and the acrid smell of burning sulfur. This invisibility poses dangers for daytime workers and visitors who might unknowingly approach active combustion zones. The sulfur miners, working primarily in pre-dawn darkness, navigate by the flame light, using the blue glow as illumination for their hazardous labor. Measuring and monitoring the blue fire phenomenon presents technical challenges. Standard photography struggles to capture the flame's true color and intensity, often resulting in images that appear artificially saturated or dimensionally flat. Thermal imaging reveals the heat signatures but misses the spectral beauty. Spectrographic analysis provides precise data on emission wavelengths but cannot convey the aesthetic impact. Scientists have developed specialized camera systems that combine multiple imaging modes to document both the scientific and visual characteristics of the phenomenon. The flame's existence depends entirely on the volcanic system's continued activity. Should the magma chamber cool significantly or the hydrothermal circulation patterns shift, the fumaroles might cease emitting sulfur-rich gases at combustible temperatures. The blue fire would disappear, transforming Kawah Ijen from a unique geological wonder into merely another acidic crater lake. This fragility adds poignancy to the spectacle, a reminder that Earth's most dramatic displays operate on temporary timescales, subject to the same forces of change that govern all natural phenomena. Recent studies have investigated whether the blue flames affect the crater's ecology in any measurable way. The short answer is that Ijen's crater possesses essentially no ecology to affect. The combination of extreme acidity, toxic gases, and unstable substrate prevents biological colonization. No plants root in the sulfur-saturated soil. No insects colonize the fumarole vicinity. No bacteria form mats in the superheated acid pools. The blue fire burns in a landscape already sterilized by chemistry and heat, adding one more layer of hostility to an environment fundamentally incompatible with life. Yet this sterility contains its own austere beauty. The crater represents Earth in a primordial state, before biology complicated the planet's surface with its demands and adaptations. Here, only physics and chemistry operate, forces that built the planet and continue reshaping it according to rules indifferent to living systems. The blue flames embody this indifference, burning not for illumination or warmth or any human purpose, but simply because the conditions permit combustion and thermodynamics demands it. Have you ever seen a volcano spew blue fire? It sounds like something out of a fantasy movie, but deep in East Java, Indonesia, this surreal phenomenon is a reality. Welcome to Kawah Ijen, a volcano that defies our expectations and glows with an eerie electric blue light. Today, we're diving deep into the science behind this incredible natural wonder. We'll uncover the unique chemical reactions and geological conditions that transform a typical volcanic eruption into a breathtaking spectacle of blue flames. What makes this particular volcano so special? And what is it like to witness this otherworldly event in person? Get ready to explore the heart of a blue inferno. Let's start by clearing up a common misconception. The blue glow at Kawah Ijen isn't blue lava. That would be scientifically impossible, as the color of molten rock is determined by its temperature, ranging from deep red to bright yellow-white. Lava simply can't get hot enough to glow blue. So, if it's not the lava, what is it? The secret lies in one key element: sulfur. Kawah Ijen is not just a volcano, it's a massive living sulfur deposit. It sits within a larger caldera and contains the world's largest acidic crater lake, a stunning turquoise body of water with a pH similar to battery acid. The volcanic vents, known as fumaroles, are constantly releasing hot, pressurized sulfuric gases from deep within the Earth's crust. These gases are the star of the show. They emerge from cracks in the rock at incredibly high temperatures, often exceeding 600 degrees Celsius or 11-12 degrees Fahrenheit. When this superheated, sulfur-rich gas comes into contact with the oxygen in the surrounding air, it ignites. This is a classic combustion reaction, but instead of burning wood or natural gas, we're burning sulfur. And when sulfur burns, it produces a vibrant, mesmerizing blue flame. Think about a gas stove in your kitchen. The flame is blue because the gas is burning completely and efficiently. The same principle applies here, but on a much grander, more dramatic scale. The blue light is a result of chemiluminescence, where a chemical reaction releases energy in the form of light. Specifically, as the sulfur atoms are excited by the intense heat, their electrons jump to higher energy levels. When they fall back to their normal state, they emit photons of light at a specific wavelength, which our eyes perceive as a vivid blue. So we have sulfuric gases and oxygen. But what makes Kawah Ijen so unique? Many volcanoes release sulfur, but few put on a show like this. The key factors are the sheer quantity and high concentration of the sulfuric gases, combined with the immense pressure and temperature at which they escape. At Ijen, the volcanic system is perfectly configured to force a massive volume of these gases to the surface, under just the right conditions to sustain this spectacular combustion. The phenomenon is most visible at night. During the day, the sunlight is so bright that it completely washes out the ethereal blue glow. But once darkness falls, the landscape transforms. The mountainside appears to be covered in rivers of electric blue fire. Now let's talk about what happens after the fire. As the burning sulfuric gas cools, it condenses directly back into a liquid state. This molten sulfur, still glowing with a reddish hue from the heat, flows down the slopes of the volcano. It looks like streams of orange lava, but it's actually pure, molten sulfur. This is where the story of Kawah Ijen takes a human turn. For decades, local miners have braved these treacherous conditions to harvest this sulfur. It's an incredibly arduous and dangerous job. The miners descend into the crater, often with minimal protection, and break up the cooled, solidified sulfur, which forms bright yellow rocks. They then load the sulfur into baskets, which can weigh anywhere from 70 to 90 kilograms, or 150 to 200 pounds. They carry these heavy loads by hand, making a grueling 3-kilometer trek up the steep crater rim and back down the mountain. The air they breathe is thick with toxic sulfuric dioxide and hydrogen sulfide gases. These gases are not only pungent, smelling of rotten eggs, but they are also incredibly dangerous. They can cause severe respiratory problems, irritate the eyes and throat, and in high concentrations can be lethal. The miners often work through the night, guided by the blue flames, as the cooler temperatures make the labor slightly more bearable. The sulfur they collect is then sold and used in a variety of industries, for everything from vulcanizing rubber and bleaching sugar to making matches and fertilizers. These miners are an integral part of the Kawah Ijen story, a testament to human resilience in one of Earth's most extreme environments. Now let's delve a bit deeper into the chemistry. The primary gas responsible for the blue flame is sulfur dioxide, or SO2. However, the volcanic gases are a complex mixture. They also contain hydrogen sulfide, or H2S. The reaction is not a single simple step. When the hot gases meet the air, a series of reactions occur. The sulfur combusts to form sulfur dioxide, which is what produces the blue light. The equation looks something like this. S plus O2 yields SO2. This reaction is highly exothermic, meaning it releases a significant amount of heat, which helps sustain the combustion process. The intense blue color is specific to the energy transitions of sulfur molecules at these high temperatures. It's a signature color, just like sodium burns orange-yellow. The landscape itself contributes to the spectacle. The rocky, uneven terrain of the crater floor forces the flowing molten sulfur to pool and cascade, creating what looks like blue waterfalls and rivers of fire. As the liquid sulfur moves, it can reignite if conditions are right, adding to the dynamic and ever-changing display. It's a powerful reminder of the raw, elemental forces at play. This isn't a controlled laboratory experiment. It's a chaotic, beautiful, and dangerous natural process. The site is so alien that it was even featured in the documentary Samsara and has been likened to landscapes on other planets. It challenges our perception of what a volcano should be. Visiting Kawah Ijen is an adventure in itself. It requires a multi-hour hike that begins in the middle of the night. Tourists and photographers from around the world make the pilgrimage, guided by local experts to witness the blue flames before sunrise. The journey is steep and demanding, and the air quality near the crater can be hazardous. Most tour operators provide gas masks, which are absolutely essential for anyone descending towards the source of the flames. Once you reach the crater rim, you're greeted with a panoramic view of the glowing blue spectacle below. It's a humbling experience to stand before such a powerful display of nature's artistry and ferocity. As the sun begins to rise, the blue flames fade, and a new marvel is revealed: the turquoise acid lake. The color of the lake is due to its high concentration of dissolved hydrochloric and sulfuric acids, which interact with the metals leached from the surrounding rock. It's a beautiful yet deadly body of water. Its extreme acidity means nothing can survive in it. The contrast between the brilliant blue of the fire at night and the stunning turquoise of the lake by day makes Kawah Ijen a place of dramatic dualities. It's a perfect example of how geology and chemistry can conspire to create some of the most stunning and scientifically fascinating phenomena on our planet. It's a world of fire and acid, of toxic gases and incredible beauty, and of the miners who risk their lives daily in its heart. So the next time you see a picture or video of Kawah Ijen's blue fire, you'll know the science behind the magic. It's not blue lava, but the magnificent combustion of vast quantities of sulfuric gases. It's a rare chemical reaction happening on a volcanic scale, creating a light show that seems to belong on another world. Kawah Ijen is a powerful reminder that our planet is still full of mysteries and wonders, waiting to be explored and understood. It's a living laboratory where the elemental forces of chemistry and geology are on full display. Thank you for joining me on this journey into the heart of the blue volcano. If you found this exploration fascinating, don't forget to like, share, and subscribe for more deep dives into the wonders of our world. See you next time. The turquoise water that fills Kawah Ijen's crater possesses a beauty that belies its lethality. From a distance, the lake appears almost inviting, its color reminiscent of tropical lagoons or alpine glacial pools. Visitors arriving at the crater rim often express surprise at the vivid hue, expecting perhaps murky brown or sulfurous yellow rather than this crystalline azure. Yet this is precisely the danger of extreme environments. Nature does not always signal hazard with ugliness. Sometimes the most hostile places wear masks of spectacular beauty. The lake's chemistry reads like a catalog of industrial corrosives. Sulfuric acid dominates the dissolved compounds, maintaining pH levels between 0.3 and 0.5, depending on seasonal dilution and evaporation rates. To contextualize these numbers, battery acid typically measures around pH 1.0, already corrosive enough to burn skin on contact. Ijen's lake is 10 times more acidic, approaching the theoretical limit of aqueous acidity. At these concentrations, the hydrogen ion activity becomes so intense that water itself begins behaving differently, its molecular structure strained by the ionic load. Dissolved metals contribute to both the lake's color and its chemical aggression. Aluminum sulfate concentrations reach extraordinary levels, leached continuously from the volcanic rocks that line the crater. Iron exists in multiple oxidation states, creating a complex equilibrium of ferrous and ferric ions that shift with oxygen availability and temperature. Manganese, zinc, copper, and trace heavy metals accumulate in quantities that would constitute toxic waste in any other context. The lake essentially functions as a natural mining operation in reverse, concentrating metals that geological processes had previously dispersed. The turquoise color results from a phenomenon called Rayleigh scattering combined with selective absorption. Suspended particles of native sulfur and precipitated metal sulfates scatter shorter wavelengths of light preferentially, while dissolved compounds absorb wavelengths in the red portion of the spectrum. The remaining transmitted and reflected light concentrates in the blue-green range, creating the characteristic color. This same physics explains why Earth's sky appears blue and why glacial ice glows with similar hues, though the specific chemistry differs entirely. Temperature stratification within the lake creates distinct zones of lethality. Surface waters average 40 degrees Celsius, warm enough to feel hot to touch but not immediately scalding. At depth, particularly near the submerged fumaroles where volcanic heat enters the system, temperatures approach boiling point. These thermal gradients drive convection currents that circulate the acidic water, preventing stable layering and ensuring uniform chemistry throughout the volume. During periods of increased volcanic activity, the entire lake can warm by several degrees, its surface roiling with vapor as heat flux from below intensifies. The hydrology of the crater involves more than simple rainwater accumulation. Groundwater seeps through fractures in the crater walls, entering the lake and contributing to its volume. Some of this groundwater has already passed through the hydrothermal system, arriving pre-acidified and heated. Springs along the lake shore discharge water at temperatures exceeding ambient, visible as zones of disturbance on the otherwise calm surface. The lake has no visible outlet, suggesting either that evaporation matches input rates or that seepage through the crater floor drains excess water into deeper aquifers. What makes Kawah Ijen's lake particularly dangerous is not merely its chemistry but its volume. 36 million cubic meters of concentrated acid represents an enormous reservoir of potential destruction. Should volcanic activity breach the crater wall or generate sufficient pressure to propel lake water beyond the rim, the resulting flood would devastate downstream communities. The acidic torrent would sterilize agricultural land, contaminate water supplies, and create a disaster zone requiring decades for ecological recovery. This scenario, termed a crater lake breakthrough or acidic lahar, has occurred at other volcanic systems worldwide, always with catastrophic consequences. Monitoring the lake requires specialized approaches. Direct sampling proves hazardous due to the acid's aggression toward equipment and human tissue. Researchers employ remote sensing techniques, using satellites and drones to track changes in lake level, temperature, and color. These measurements provide early warning of potential volcanic unrest. A sudden temperature increase might indicate rising magma. A drop in lake level could signal increased evaporation from elevated heat flux, or potentially more concerning subsurface drainage that weakens the crater structure. The lake's complete sterility deserves emphasis. No organism, regardless of adaptation, survives in Kawah Ijen's crater lake. Extremophile bacteria that thrive in hot springs, acid mine drainage, and other hostile environments cannot establish populations here. The combination of extreme pH, high metal concentrations, and elevated temperature exceeds even the most resilient biological tolerances. This makes the lake one of Earth's few genuinely lifeless water bodies, comparable only to the Dead Sea in salinity-based sterility or certain Antarctic subglacial lakes isolated from biological input. Yet even in sterility, processes continue. Chemical reactions proceed according to thermodynamic imperatives. Sulfur precipitates and redissolves. Metals cycle through oxidation states. Gases bubble from submerged vents, disturbing the surface with ephemeral patterns. The lake exists in dynamic equilibrium, balanced between volcanic input and atmospheric loss, between heating and cooling, between concentration and dilution. It stands as testament to chemistry's power to create environments fundamentally incompatible with the biological world. Reminders that Earth's surface includes zones where life's foothold remains tentative at best and entirely absent at worst. To understand Kawah Ijen requires stepping back from the particular to examine the vast geological context that makes its existence possible. Indonesia sits astride one of Earth's most volcanically active regions, a zone where planetary forces converge with consequences both creative and catastrophic. The nation contains more active volcanoes than any other country, over 120 volcanic centers that have erupted within recorded history, a concentration of fire mountains that results directly from its position along tectonic boundaries. The Pacific Ring of Fire encircles the world's largest ocean in a horseshoe of volcanic and seismic activity. This zone, stretching from New Zealand through Indonesia and Japan, across to Alaska and down the western coasts of North and South America, accounts for approximately 90% of Earth's earthquakes and 75% of its active volcanoes. The ring exists because oceanic plates that form the Pacific Basin floor collide with and descend beneath continental and island arc plates in a process called subduction. At the Indonesian segment of this ring, the Australian plate moves northward at approximately 7 centimeters per year, driven by convection currents in Earth's mantle. Where this plate meets the Sunda plate upon which Indonesia rests, the denser oceanic crust of the Australian plate dives beneath the lighter continental material. This descent occurs at an angle, the subducting slab penetrating to depths exceeding 600 kilometers in some locations. As the plate descends, pressure and temperature increase, driving water and volatile compounds from the oceanic crust and overlying sediments. These released fluids rise into the mantle wedge above the subducting slab, lowering the melting point of the rock and generating magma. The newly formed melt, being less dense than surrounding solid rock, rises buoyantly toward the surface. Where this magma reaches the crust, it either erupts explosively at volcanoes like Kawah Ijen or cools slowly underground, forming plutonic bodies that may eventually be exposed by erosion. The entire Indonesian archipelago owes its existence to this process, a chain of volcanic islands built incrementally over millions of years. The magma that feeds Ijen and its neighboring volcanoes differs in composition from the basaltic magma that forms oceanic crust or the effusive flows of Hawaiian volcanoes. Subduction zone magmas are andesitic to dacitic, enriched in silica and volatile compounds including water and sulfur dioxide. This composition makes the magma more viscous, trapping gases that build pressure until explosive release becomes inevitable. The resulting eruptions produce ash clouds, pyroclastic flows, and the stratified deposits that construct stratovolcanoes. Java's position at the convergent boundary creates exceptional volcanic density. The island hosts 45 active volcanoes, mountains that have shaped human history as profoundly as they have shaped the landscape. Merapi Kelad, Semeru, Krakatau. These names resonate through Indonesian culture. Mountains that provide fertile soils for agriculture while periodically destroying the communities that depend on those soils. The bargain is ancient and unbreakable. Volcanic regions offer exceptional productivity between eruptions, supporting population densities that accept periodic catastrophe as the price of prosperity. Kawah Ijen belongs to a cluster of volcanoes in East Java, part of the Ijen volcanic complex that includes several peaks sharing a common magmatic system. The complex sits within the Ijen caldera, a depression formed by a massive eruption approximately 50,000 years ago. That ancient explosion ejected an estimated 80 cubic kilometers of material, leaving a crater 20 kilometers wide. Subsequent volcanic activity has partially filled this caldera, creating the younger cones visible today. The current activity at Kawah Ijen represents a relatively quiet phase in the volcano's history. The last confirmed magmatic eruption occurred in 1817, producing lava flows and modest ash emissions. Earlier eruptions in 1796 and 1817 caused fatalities and property damage, though nothing approaching the scale of disasters at neighboring volcanoes. Phreatic eruptions, driven by steam explosions when groundwater contacts hot rock rather than rising magma, have occurred more recently, most notably in 1936, 1952, and 2000. This relative quiescence should not inspire complacency. Volcanic systems operate on timescales that dwarf human planning horizons. A volcano quiet for 2 centuries may be approaching its next eruptive cycle, or may remain dormant for millennia more. The magma chamber beneath Ijen continues receiving fresh magma from depth, evidenced by ongoing degassing and geothermal activity. The system remains active, merely expressing that activity through sulfur emission and acidic lake chemistry rather than explosive eruption. The monitoring network surrounding Kawah Ijen reflects modern volcanology's capabilities and limitations. Seismometers detect earthquakes caused by magma movement and fracturing rock. GPS stations track ground deformation with millimeter precision, identifying the swelling that precedes magma ascent. Gas sensors analyze fumarole emissions for compositional changes that might indicate rising magma, bringing deeper gases to the surface. Thermal cameras track heat signatures across the volcano's flanks. Satellite radar provides broad-scale monitoring of ground movement, yet prediction remains imperfect. Volcanoes exhibit precursor signals before some eruptions, while others begin with minimal warning. The same earthquake swarm might herald imminent eruption or subside into renewed dormancy. Ground deformation might indicate magma intrusion at depth or simply hydrothermal expansion. Gas composition changes might reflect new magma or shifts in the shallow hydrothermal system. Volcanology has advanced tremendously in recent decades, but Earth's interior still guards its intentions, revealing them only when pressure and chemistry leave no alternative to violent release. The transformation of Kawah Ijen from remote sulfur mining site to international tourist destination occurred gradually, then suddenly. For decades, only miners and occasional researchers visited the crater, accessing it through difficult trails that required local guides and considerable physical fitness. The volcano existed in relative obscurity, known within geological circles for its acidic lake and sulfur deposits, but absent from mainstream travel itineraries. The catalyst for change arrived through photography. In the early 2000s, adventure photographers began documenting the blue fire phenomenon, producing images of such startling beauty that they circulated widely through emerging social media platforms and photography websites. The electric blue flames juxtaposed against miners silhouetted in the toxic glow created visuals that seemed almost digitally manipulated, too dramatic to represent unaltered reality. Yet the images were genuine, and they generated fascination that translated into tourism demand. By 2010, visitor numbers began increasing noticeably. Adventurous travelers added Kawah Ijen to East Java itineraries, often combining it with visits to Mount Bromo, another photogenic volcano nearby. Tour operators recognized the opportunity and established overnight trips that positioned visitors at the crater rim before dawn to witness the blue flames. The logistics were straightforward. Transport tourists to the base at midnight, guide them up the trail in darkness, allow several hours for photography and observation, then descend before midday heat made the trek unbearable. Infrastructure developed to accommodate the influx. The access road improved, though it remained challenging enough to maintain Ijen's adventure tourism character. A registration and ticket office appeared at the trailhead, formalizing what had previously been informal arrangements with local communities. The trail itself received upgrades including concrete steps on the steepest sections and periodic rest stations. At the crater rim, viewing platforms provided safer vantage points than the informal positions visitors had previously occupied. The economic impact rippled through surrounding communities. Villages that had subsisted on agriculture and sulfur mining gained new income sources through tourism services. Locals became guides, drivers, porters, and accommodation providers. Small restaurants and shops catered to pre-dawn hikers needing coffee and snacks. The transformation was not uniformly positive. Tourism created economic dependency and seasonal income fluctuations, but it provided alternatives to sulfur mining's physical destruction. The interaction between tourists and miners created complex dynamics. Visitors paid entrance fees exceeding what miners earned daily while photographing men whose labor they romanticized but would never themselves undertake. The miners became involuntary performers in a spectacle they did not control. Their suffering aestheticized by camera lenses that captured dramatic images while remaining safely distant from the reality those images represented. Some miners resented this commodification. Others pragmatically accepted tips for posing or allowing close-up photography, supplementing meager sulfur earnings with tourist money. Environmental concerns accompanied increased visitation. Hundreds of daily visitors stressed the fragile volcanic ecosystem such as it was. Trash accumulated despite nominal cleanup efforts. Trails eroded under constant foot traffic. The crater rim showed signs of degradation as visitors ventured beyond designated areas seeking better photography angles. The toxic environment paradoxically proved vulnerable to human impact, its chemical hostility not protecting it from physical disruption. Safety incidents became inevitable as visitor numbers grew. The combination of pre-dawn darkness, steep terrain, toxic gases, and inadequate physical preparation created accident conditions. Tourists occasionally suffered falls, respiratory distress from gas exposure, or altitude-related problems despite Ijen's modest elevation. Most incidents involved minor injuries, but several serious accidents occurred, including fatalities when visitors ignored barriers or ventured too close to unstable crater walls. Regulatory responses evolved slowly. Local authorities implemented permit systems limiting daily visitor numbers, though enforcement proved inconsistent. Requirements for licensed guides aimed to improve safety and ensure visitors understood the risks, though guide quality varied considerably. Mandatory safety briefings at the registration office informed visitors about toxic gas dangers and proper behavior near the crater. Though their effectiveness depended on individual compliance, The blue fire itself became a victim of its fame. The best viewing occurred in pre-dawn darkness when flames were most visible, creating concentrations of sometimes hundreds of people crowding the crater floor simultaneously. This gathering occurred in the same toxic environment where miners worked, creating congestion that impeded both tourism and mining. Photographers jockeyed for positions, sometimes blocking miners carrying sulfur loads up the narrow trail, conflicts that highlighted the uncomfortable coexistence of economic exploitation and recreational consumption. Paradoxically, tourism increased awareness of mining conditions while doing little to improve them. Documentaries and articles highlighting the miners' plight generated international attention and charitable efforts. Some organizations initiated programs providing better safety equipment or alternative employment training. Yet the fundamental economics remained unchanged. Sulfur prices stayed low, mining wages stayed minimal, and men continued descending into the crater because no better options existed. The COVID-19 pandemic brought temporary cessation to tourism in 2020 and 2021, providing an inadvertent case study in Ijen's ecology without visitors. The crater rim vegetation recovered somewhat. Wildlife returned to areas it had abandoned when human traffic intensified. The sulfur mining continued unabated, demonstrating that tourism was supplementary rather than essential to local economies. When restrictions lifted and visitors returned, they found Ijen largely unchanged, the volcano indifferent to the interruption in human attention. Modern volcanology represents humanity's attempt to predict the unpredictable, to impose pattern recognition and probability assessment onto systems governed by forces that operate beyond human timescales and beneath human observation. At Kawah Ijen, this effort manifests through an array of instruments and monitoring protocols that transform the volcano from inscrutable natural phenomenon into a partially readable text, one written in the language of seismic waves, gas emissions, and ground deformation. The Center for Volcanology and Geological Hazard Mitigation, Indonesia's primary volcanic monitoring agency, maintains continuous surveillance of Kawah Ijen alongside the nation's other active volcanoes. This surveillance operates at multiple scales, from satellite observations tracking thermal signatures across the entire volcanic complex to ground-based sensors, measuring minute changes in local seismicity. The integration of these data streams provides volcanologists with a multi-dimensional portrait of the volcano, current state, and potential trajectory. Seismic monitoring forms the foundation of this surveillance network. Earthquakes occur continuously beneath active volcanoes, generated by magma movement, rock fracturing under stress, and hydrothermal fluid circulation. The character of these earthquakes reveals information about their sources. Volcanic tectonic earthquakes, caused by rock breaking under pressure, produce sharp signals with clear P&S wave arrivals. Low-frequency earthquakes, generated by fluid movement through cracks and conduits, create signals that lack the sharp onset of tectonic events. Harmonic tremor, a continuous oscillation, indicates sustained fluid movement and often presages eruption. At Ijen, seismometers detect approximately 20 to 60 earthquakes daily during baseline conditions, a level of seismicity considered normal for an active hydrothermal system. These events typically register below magnitude 2.0, too small for human perception but readily detected by sensitive instruments. The earthquake locations, determined by comparing arrival times at multiple seismometer stations, cluster beneath the crater and along the flanks, mapping the fracture network through which gases and heated groundwater circulate. Changes in seismic patterns provide early warning of potential volcanic unrest. An increase in earthquake frequency might indicate rising magma pressuring surrounding rock. Migration of earthquake locations toward shallower depths could signal magma ascent. The appearance of harmonic tremor suggests fluid movement on a scale that might precede eruption. Volcanologists monitor these patterns continuously, comparing current activity against historical baselines to identify anomalies requiring heightened alert levels. Ground deformation monitoring employs GPS stations and satellite radar interferometry to detect swelling or subsidence of the volcanic edifice. Magma accumulation in subsurface chambers pushes surrounding rock outward and upward, creating measurable deformation. At Ijen, GPS stations positioned around the crater and on the flanks measure position changes with millimeter precision. The data reveal slow, ongoing deformation consistent with hydrothermal activity and minor magma recharge, but nothing indicating imminent eruption. Satellite radar interferometry complements ground-based GPS by providing broader spatial coverage. Satellites orbit Earth repeatedly, imaging the same areas from identical positions. By comparing radar images acquired months or years apart, scientists detect ground movement too subtle for conventional surveying. This technique, called INSAR, has revolutionized volcano monitoring by revealing deformation patterns invisible to ground-based sensors. At Ijen, INSAR data show minor inflation and deflation cycles related to hydrothermal system dynamics rather than magmatic processes. Gas monitoring provides direct sampling of volcanic emissions, offering chemical fingerprints that reveal processes occurring deep within the volcano. The composition of fumarole gases reflects the sources contributing to the emissions. High concentrations of sulfur dioxide indicate magma degassing at depth. Increased carbon dioxide ratios suggest deeper magmatic contributions. Helium isotope ratios distinguish mantle-derived gases from crustal sources. At Ijen, regular gas sampling shows compositions dominated by hydrothermal fluids rather than fresh magmatic gases, consistent with the volcano's current quiet eruptive state. Thermal monitoring tracks heat flux from the crater using ground-based infrared cameras and satellite thermal sensors. Temperature changes can indicate shifts in the hydrothermal system or rising magma introducing additional heat. The acidic lake itself serves as a thermal integrator, its temperature responding to heat input from below. Satellite thermal sensors measure lake surface temperature remotely, detecting changes that might signal increased volcanic activity. Recent data show temperatures fluctuating seasonally but without sustained increases that would suggest magmatic unrest. Visual observation remains valuable despite technological advances. Local residents and sulfur miners spend more time near the volcano than any scientist or instrument. They notice changes in gas emissions, unusual sounds from the crater, or behavioral anomalies in animals that may flee before eruptions. Effective monitoring programs incorporate these observations, recognizing that human presence provides continuous surveillance instruments cannot match. The monitoring data feed into a volcanic alert level system with 4 ascending stages: normal, advisory, watch, and warning. Each level corresponds to specific observed conditions and triggers predetermined response protocols. At normal level, baseline monitoring continues without special restrictions. Advisory level activates when anomalous activity suggests possible escalation toward eruption. Watch level restricts access to hazardous zones. Warning level indicates eruption is imminent or underway, triggering evacuations. Kawah Ijen currently maintains normal status, though volcanologists emphasize that this designation reflects current conditions rather than guaranteed future behavior. The volcano's monitoring network provides reasonable confidence in detecting significant changes before eruption, though the warning time might range from weeks to mere hours depending on how the volcano behaves. The goal is not perfect prediction, but rather sufficient warning to implement protective measures that minimize casualties when eruption becomes inevitable. The relationship between humanity and volcanoes represents one of civilization's oldest and most complex negotiations. Across Indonesia and throughout the Ring of Fire, millions of people live within volcanic hazard zones. Their presence a calculated gamble that weighs fertile soils and economic opportunity against periodic catastrophe. This proximity is not ignorance or fatalism, but rather a sophisticated risk assessment that recognizes volcanic regions offer prosperity, unavailable in geologically stable areas, provided communities accept that prosperity as temporary and conditional. Around Kawah Ijen, villages occupy the middle and lower slopes, where volcanic soils produce exceptional agricultural yields. Coffee, rice, vegetables, and tropical fruits grow with minimal fertilization in earth enriched by millennia of volcanic ash deposition. These communities have existed for generations, long enough to develop cultural practices and oral histories that encode volcanic knowledge. Elders remember previous eruptions or recall stories passed from ancestors, maintaining institutional memory that supplements scientific monitoring. The economic calculus of volcanic proximity extends beyond agriculture. The sulfur mining industry, despite its brutal working conditions, provides employment where alternatives remain scarce. Tourism brings additional income, creating service sector jobs that allow some families to escape the physical toll of farming or mining. The volcano that threatens also sustains, a duality that shapes local attitudes toward risk and resilience. Hazard awareness varies considerably across communities. Villages close to Ijen generally demonstrate higher awareness and better evacuation preparedness than more distant settlements that face lower immediate risk, but might still experience ashfall or layers during major eruptions. Government agencies conduct periodic disaster preparedness drills, establishing evacuation routes and designated safe zones. Participation in these drills fluctuates based on recent volcanic activity, high after eruptions elsewhere in Indonesia, lower during extended quiet periods when complacency returns. The challenges of volcanic risk communication deserve examination. Scientific uncertainty about eruption timing and magnitude complicates efforts to convey hazards to non-technical audiences. Volcanologists cannot definitively state when Kawah Ijen will next erupt or how severe that eruption will be. They can describe scenarios, assign rough probabilities, and identify precursor signals, but prediction remains probabilistic rather than deterministic. Communicating this uncertainty without either understating risk or creating panic requires careful language and sustained engagement with communities. Indonesia's experience with volcanic disasters informs current preparedness strategies. The 1815 eruption of Mount Tambora killed an estimated 71,000 people and caused global climate disruption.